As you're now well aware of, the area under a curve, say f, from a to b is the integral from a to b of f of x dx, provided that f is 0 or greater, right? F is not negative. What about the area between two curves, f and g? In order to develop what's going on with that, let's look back here at the area under f. Remember that we started out looking at area as based on areas of a bunch of rectangles. And each of the rectangles had a width of delta x and a height that was, say, f of x sub I. Then we said the area of the ith rectangle is f of x sub I times delta x. And then we added together n of these, and then let n go to infinity, and that's where the integral came from. Over here, where we're looking at f and g, what's really going on with our integral is that we're taking the area of a rectangle whose height is determined by f. So we're looking at f of x sub I times delta x. And then we're going to subtract off the area of a rectangle whose height is given by g and whose width is that same delta x. And the same limit process is going to happen as before. We're going to add together n of these expressions and then let n go to infinity. The result is the following. The area A of the region bounded by curves y equals f of x and y equals g of x, and the lines x equals a, x equals b, where f and g are continuous, and f is at least as big as g for all x in the interval from a to b, is a equals the integral from a to b of the integrand is f of x minus g of x dx. That's this picture here. And what's not in my picture is that this goes from a to b. Although this a and b are, I made them the points of intersection between f and g. This a and b could be closer together, wider apart. It doesn't really matter. What does matter is f is the one that's on top, it's bigger. G is the one that's on bottom, it's smaller. And I have f minus g. Area is always going to be positive, right? In practice, we're not going to do the integral of f and then the integral of g unless it's just advantageous to do so. Generally speaking, we're going to simplify the integrand and then integrate. This similar thing can be said about functions of y. Well, here we have f and g are both functions of x, right? We could very well have a situation where we would prefer everything to be in terms of y. And here's an example of such a situation. So suppose we wanted the area between these two curves. I don't really want to do this in terms of x for a couple of reasons. Number one, this curve is not a function of x. And number two, if I did that, I would actually have to split the region right here and set up two separate integrals. And that's just not necessary if we consider, let's say this is f of y and the line is g of y. Right? So we have this like parabola on its side. That's what I'm calling f of y. And then we'll say that the points of intersection have y coordinates of c and d. Now this is a little weird because we're used to looking at x coordinates here, but these are y coordinates. The area here is going to be the integral from c to d of f of y minus g of y dy. And we just integrate in terms of y, and that's totally fine. What comes up, though, is how do I know whether g should go first or f should go first? Well, we're very used to looking at functions of x and knowing that the orientation is that up is bigger for y, right? On the y-axis, up is positive, and if f is above g, then we know that f is bigger than g. When our functions are functions of y, we need to keep in mind that on the x-axis, to the right is positive, right? On the x-axis, for instance, 5 is to the right of 3. 5 is bigger than 3. So whichever function is the rightmost function, that's the one that's biggest. And then the one that's the leftmost function for the region that we're talking about. That one is smallest.